And so today, Nicola Dondi is going to tell us about large charge expansions and their asymptotics.
Okay, so thank you very much, the organizer first, for allowing me to speak about my work. So today I'm going to talk about this topic of large charge expansion. These are joint work with the group in Bern, led by Domenico and Susanne Reffert, and together with some PhD students as well in, got it, right? Okay. All in Bern University. This is a mixture of work that you can find in the first paper from last year, but also a lot of improvement which went on unpublished and on some extensions that we are currently working on. Okay. And please, if you have any question, don't hesitate to interrupt me. I like to have it also as a lively discussion, but let's see how it goes. So, okay. So my outline is basically divided in 4 sections. So at the beginning, I wanted to give like a sort of friendly, see how friendly it is, introduction to this idea of large charge expansion in conformal field theories. I will show a bit how historically this has developed. Historically means like since 6 years ago, 6-7 years ago. You will see that these large charge expansions are sort of a bottom-up approach to computation in conformal field theories. And most of the time, we will find that we have series. We can expand our observables in series, but the coefficients are unknown. To solve that and try to attempt a resurgence analysis for all this quantity we compute, we actually use some specific model, is more of a top-down approach, and use some specific double scaling limit. I will make a large use of large Yang methods that you see already yesterday. And discuss mostly in the example that by now we worked out quite in detail, which is the ON critical model, and then offer my conclusion at the very end. Okay, so let's start with the slide 0 of introduction. What do I mean with conformal field theory? So this is meant to be as friendly as it gets, but don't hesitate to stop me. So a conformal field theory is just a quantum field theory that has an enhanced space-time symmetry group. Instead of having just Poincare, has the entire conformal group of RD. I'm mostly looking at field theories that live in flat space-time. Okay. So the conformal group of RD, you can think of it as normal Poincare plus scaling and some extra transformation called special conformal. But the main generator that you should care about is this scaling generator. These theories are quite special, okay, just because they have this enhanced symmetry. Namely, they don't have any scale, okay, and you don't have renormalization as in the conventional sense as you've seen before. So there is not going to be any renormal in this talk, okay. And this theory, this symmetry is so constraining that basically any CFT can be determined by a minimal set of information, which is a set of operators, OI, that I call here. These are also known as primaries. They are the one from which you can build the entire representation of the conformal group. Okay, so minimal set of operators acting on my Hilbert space. They all come attached with a scaling dimension, a number, real number called delta I, which is the eigenvalue of this scaling operator, this new symmetry that we introduced. On top of that, you also have, these are called OPE coefficients, and are basically extra number you need to specify in order to have all possible correlators computed in a CFT. In fact, conformal invariance is so strong that completely fixes 2-point function and 3-point functions in terms of these numbers. Okay. These numbers are real. These delta I especially are larger than 0. Actually, they are bounded from below. And the main problem, I mean, aside from having a lot of application, these sort of models, like you can use it to classify quantum field theories in generals, because we all believe that at the end of our G flows, conformal field theories lies at these fixed points, and you can classify all of these running QFTs by a CFT deformed so where you break scaling, basically. But also has a lot of application in critical phenomena and con-math system. For example, yesterday we had a talk about percolation theory, and the main goal of that talk exactly was to compute a scaling dimension delta for one specific critical theory, which aims to describe percolation theory. Now, generically, these conformal data, this set of numbers, delta I and lambda ijk, are hard to compute ab initio. There are perturbative methods like epsilon expansions. These perturbative methods all rely on the fact that I can study a CFT, which is arbitrarily close to the very simplest example of CFT that we know, which are free theories. Okay. However, there are also other methods like largen. Largen is semi-perturbative because some operators will have a scaling dimension which deviates slightly from the free theory value, but some others instead that already gets order 1 contribution from it. But this is the main problem of main computational problem in this model. Once you're able to compute this conformal data, basically all the correlators can be computed and all prediction can be made already from there. Okay. Now I want to now discuss a little bit what is known about the generic spectra of QFT. This is a nice picture that I stole from this paper, which I think is actually pretty nice. So in this graph, we have 3 axes in which we put the scaling dimension of operators, the spin of an operator, which is basically labels the representation under the rotation group in Euclidean space, and quantum number Q, which now I just labeled by Q, which is associated to any possible global symmetry that my CFT can have. Any point in this 3D plot is an operator, and all of these numbers should be computed accordingly. So let me start describing like this first plane, the delta versus J. So over there is this stark line that you see over there is called the unitarity bound. It means that basically any CFT which is also unitary cannot have any operator line below that line. Okay, and at the very origin here, there is one operator, which is the identity operator, which is always there. Yes, and I cannot use it because it's not connected. I know. I mean, I can still analog version, but at the origins, it's this identity which has a 0 scaling dimension, no quantum number associated to anything, and is a scalar, so no spin. The operators lying in that neighborhood are, I will call them light, meaning that they have a low scaling dimension. These are all real numbers, so for me, 1, less than 1 means a light. And those are the hardest to compute. However, recently it has been shown that in the heavy operator sectors, there are some methods, some specific methods that can give very general prediction on how these quantum numbers behave or what kind of spectra we should expect in the neighborhood of that regions. For example, there's been a lot of work in large J expansion, so large spin. Names are, for example, Dai and Dissi. If you're in the region in which you have scalar operators with no associated quantum numbers, but very heavy ones, then there are these methods called Tauberian theorems. The spectra over there is exponentially growing. There is a lot of states. There's a lot of operators there. But now, what I'm actually most interested for this talk is this other region, this large charge region. So these are operators which are heavy and have very large quantum numbers with respect to the symmetry, to the global symmetry group. So if the global symmetry group is a O2 or U1, you can think of this really as a charge, as just the charge of the operator, and you can think it to be large. If the group is non-abelian, you should think of it as a larger representation, okay? Possibly symmetric. In this talk, I'm going to talk about large symmetric representations. Now, here, there is this dotted line, which is not a unitarity bound, okay? But one I think of the main results of this subject is exactly the fact that below this dotted line, again, there is no operator, okay? Even though there is no a priori reason for it to be, okay? But under very mild assumption, you can show that this is the case. So let's talk a bit about this specific sector. One of the main tools that you need to use to try to describe this sector is the so-called state operator correspondence. It basically works in CFTs for the simple reason that now, if you're in RD and you are conformal, you can decide, instead of foliating via planes, like you do in normal quantum mechanics or quantum field theory, you can start foliating by sphere, so radially. You can use a conformal isometry to do that. And Hilbert spaces will start living on spheres. And the Hamiltonian in that case is going to be exactly my dilation operator. Intuitively, this has an intuitive picture that as I dilate, I move to larger and larger spheres. This practically is implemented via Weyl transformation, under which all CFTs are invariant up to anomalies, but I will talk about odd dimensions. And what happens here is that for any of these primary operators that I have in my RD CFT, if I act on a vacuum, they will generate, among all the possible states of my CFT, they will generate one particular one, which is going to be a primary state. And moreover, all the power law correlators of the two-point functions can be actually written as decaying exponential on the cylinder. The time tau is the cylinder time. Okay. And to prepare for what's going on, I will start introducing some thermodynamics lingo, namely, for these two-point function, maybe most of the time is not really convenient to start from the state really that you want to pick up with, but you might decide to start from tracing out over all possible states with similar quantum numbers. And that you can do, for example, by make it thermal. Basically, take this cylinder, the correspondence works only on the cylinder, but I can think of compactifying it into a torus and at the very end of my computation, send this radius of the torus to be infinite. This is also known as, is also an inverse temperature, this beta parameter, this length of the torus, okay? So from now on, if I say temperature, inverse temperature, I'm going to talk about beta in this setup. And one way, for example, that we have in this setting to compute a scaling dimension is to actually trace over all the Hilbert space on the cylinder with some sort of projector. This projector is meant to enforce some constraints, like I only care about operators with these and that quantum numbers. And in the limit in which I take my torus to go back to the cylinder, this expression is going to spit up the lightest one, okay? So that's why I write delta mean. Okay, this is the smallest one with the possible quantum number enforced by this projector. This is quite maybe artificial, but helps a lot, at least in the intuition that comes below. And these particular trace, you can also identify it as a partition function for a thermal system with a given charge density. Okay. So this is a formula that also was flashed around yesterday. It's very similar to what we see already. Now, what is the main? So the main point of this large charge expansion is that these partition functions, right, can be computed in a bottom-up approach. Namely, if I want, for example, to select only states or operators which have a quantum number q, formally, right, I introduce a delta function for it, which means only sum over the states or operator with those quantum numbers. And the main statement is that as this charge goes large, okay, this partition function can be computed by an EFT. An EFT is an effective field theory, okay, which captures most of the features that we expect for the system to have, but has limitations, okay? And this particular EFT is very peculiar. At least in bosonic system has been shown to be the EFT for a Goldstone boson, which realized this particular symmetry breaking pattern. Okay, so if you're not familiar with what a symmetry breaking patterns means basically that this is the symmetry of my original theory. This is the unbroken symmetry, meaning the one that is still linearly realized on my fields. All the others are still there, but they're not linearly realized, okay? And EFT generically, they only work in a given range of energy scales. And these energy scales, they are cut on the cylinder, as long as we're on the cylinder, have an IR cutoff, which is the maximum wavelength that you can have on your cylinder. But they also have an upper cutoff, which is given by the density of my charge quantum number Q. So only in the limit in which the charge is very large, this is a good hierarchy. So I have a good validity range for my EFT, okay? That's why I need Q much larger than 1. Now, for bosonic theories, bosonic interacting CFT theories, has been shown that this action can be very weird looking, has a very unusual kinetic term to the power 3/2. That is to ensure that you still realize conformal symmetry, just in a nonlinear way. And basically, the problem for the bottom-up character of this approach is that the leading term plus all the other ones that I can put by symmetry are all multiplied by a constant, also known as Wilson coefficients, which knows about which CFT you're starting with. This is meant to be sort of a universal result for any CFT that has this particular large charge sector, but which particular one is decided by these numbers, okay? Now, I can already give like 2 examples in which this doesn't happen. One is the free boson. So the free boson CFT doesn't have a large charge sector that works this way, and that's due to the shift symmetry that the Lagrangian has. Another one is the free fermion, okay? The free fermion has a non-trivial large charge sector for charge U1 or O2 symmetry, but is not described by a superfluid. It's described by a Fermi sphere, okay? So it's already slightly different. There are exceptions. Yes. Yes, I'm sorry. Yeah, because from the next slide on, D is gonna take into B3. But yes. So here, this is meant to hold for generically, generic odd dimension. In even dimension, you have also anomaly terms, which are, however, subleading in my large charge expansion, but you should be aware that they are there. Okay. Very good. So the point here is exactly this one. So this EFT will compute my scaling dimension and my OP coefficient, okay, as a series in inverse power of the charge. This is what this EFT is designed to set up. Problem is that we have to commit to some model and be able to compute this coefficient at this point, okay? So let me also maybe tell you also that like predictions of this EFT approach has been tested in the O2 Wilson Fisher CFT. This is for ConMat people is the XY system, spin system with the O2 symmetry at the critical point is described by this CFT, and it leads to a stark prediction for the scaling dimension of the lowest operator with a very large O2 charge. Namely, the leading term is going to go like Q to the 3/2. This is exactly the curve that I was showing before, and that actually is also here. And it's going to be organized in powers of actually Q inverse power of Q with an offset of square root of Q. Now, Monte Carlo method have tested this prediction for the minimal operators, okay, and seems to fit quite good with the accuracy. I'm not sure that already have been tested a second prediction, namely this EFT has a ground state, and this ground state computes exactly the scaling dimension, but you have fluctuation on top, and these fluctuation on tops are known as in conmat as the superfluid phonons. So physically they are just shock waves moving in a superfluid. And they all will be related to other primaries, okay? Other primaries operator which are slightly heavier than these minimal operators. They all carry a spin, and they are predicted to be there. They are predicted to have order 1 gap among each other, but these are also needs to be tested. Now, the main question that I want to ask in this talk is what kind of expansion are we expecting in an actual CFT, right? Are we expecting these large charge expansion to be convergent, divergent? What can we say about it? And moreover, there is a lot of hints, especially from the Monte Carlo data, that this extrapolation, which should hold only for very large values of my quantum numbers, seems to extrapolate pretty neatly also to order 1 charges. These are light operator with small quantum numbers, and there is no a priori reason why these EFT should hold up to order 1.
Sorry,
yes.
Can you explain this quick fact? So how would you this line? How this line has been more precisely obtained?
So they have basically took they were able to compute 2-point controlators for operators with charge 1, 2, 3, 4, get all these points. The points are the MC data with a they have a very small error. And from just the first 2, or I don't remember, I think the last 2 that they got, they were able to give an estimate for the first 2 coefficients up there. And from that, they get the fit.
So this fit is the first 2 coefficient of this formula?
Yes, for the first 2 coefficient of this formula.
It works up to Q equal to 2.
Yeah. Yeah. I mean, at least in the example that I'm going to show, might become clear why that the problem starts to get like really close to 0, but there are no real operator with that charge, right? So, yeah. So this is one, and eventually one might expect to find also exponential corrections. Okay, if my series is asymptotic, they will naively be there. They have been work, especially in supersymmetric theories, showing that this type of correction can be there, and all of these sort of questions basically are the thing that I'm going to try to give an answer in this talk. Okay, so how do I do if I cannot compute those coefficients using Monte Carlo methods? Okay. So I will basically specify a model which becomes weakly coupled in a sense, and try to give a closed form expression for these coefficients in this limit. So let me start by some definition. So first, I just show you that the partition function that you should use to compute this scaling dimension is the one that you see in the book as the one in canonical ensemble. Meaning your free parameters are temperature, the volume, which is finite, being on a cylinder, and charge density. It turns out to be much more convenient to work in a grand canonical ensemble in which you trade your dependence for Q for a chemical potential. Okay. The two are related just by a Legendre transform. This Legendre transform is gonna come out later and is gonna be like a source of annoyances at some point. But for the moment, let's just try to compute a grand canonical partition function for a specific CFT. So the CFT that I'm looking at is the O2N critical model in large N. Okay. It has an action which on the cylinder is written in this form in terms of a complex field, which is a SUN fundamental representation. If you split up real and imaginary part, you see that this symmetry is actually enhanced to O2N, but just out of convenience, I use a complex representation. Has an auxiliary field sigma, is called an Haber-Startanovich field, is commonly introduced when dealing with large N CFTs. The main thing that it's doing basically is telling that at the CFT, this singlet operator is not there, is decoupled, and its place is taken by sigma. Okay. And moreover, you should also be aware that there is a coupling to the curvature. It's called a conformal coupling. It needs to be there in order to recover the correct Weil invariance on the in curve space. But other than that, there's not much. Okay. So the action is quite, yes.
Sorry, you were a bit fast because sigma should have a term which is sigma square.
Yes.
And which at the CFT point should be relevant, and then you neglect. But
yes.
Here it's not clear whether you are already at the fixed point. Can you?
I am already at the fixed point. So in principle, this is a 5-4 theory with and here you're going to have a sigma square term. And once you integrate out again sigma, you're going to get back your 5-4 theory. Here I already took the critical limit. So that's why this is only the critical action for the ON. In principle, actually, all of this computation goes through even if you stay off criticality. But it actually might be easier that there shouldn't be any renormalization, I think, for that coupling at the leading order in N. So you can keep it that coupling to be just a parameter, an extra parameter. You can go through it. But for the moment, I only want to stay at the critical point. Okay. Yeah. And okay, so to put it at finite density, we couple to a chemical potential. The chemical potential coupling is done with is modeled by a special covariant derivatives with only shifts by a constant connection, the time derivative, the cylinder time derivative. While all the derivatives in the direction tangent to the sphere are the usual ones. Okay. So this critical model at finite chemical potential. The only task that we have is to try to compute this partition function. Okay. So first, I should tell you what am I sourcing. Okay. So I told you before, like, okay, I can put like some sort of projector in my partition function that selects what I want. Here, it doesn't look that intuitive. But what I'm doing with this chemical potential sourcing, which is identical for every boson species, is to source a diagonal subgroup, a abelian subgroup of the all O2N symmetry. Okay, so I am really in a abelian sector of my CFT operators, and you can show that this is the correct boundary condition sourcing this specific operator. So in a complex field representation is just phi to the q, right? So as q gets large, of course, this is a very heavy operator in general. And in a O2N invariant fashion instead is the one with the Young tableau, which is completely symmetric and with a very large number of boxes. Okay. I also should say that this computation has also been done in flat space, right? Without relying to all of this machinery. You compute a 2-point function of this operator, and you get the same expression for its scaling dimension. The gain, at least in my opinion, the gain of doing this computation on the cylinder is that it's gonna actually show us that there is in fact like a superfluid effective field theory for this partition function. Okay. However, of course, we have to make the theory somehow weakly coupled or accessible to computation enough. And the way to do it is to define a specific double scaling limit in which not only n is taken to be large, but also the charge of this operator is, in a way that the ratio is constant. So by now, from the next slide on, everything that has a hat is normalized by n and is finite in this limit. Okay. This is my effective tooth coupling. Okay. Okay. I'm doing time. Oh, okay, very good. So the way that people do this sort of computation, of course, in these larger limits for this partition function is to look for a saddle. Now, it's easy to see that, well, it's not immediate, but you can show that by conformal invariance, the saddles for these fields in large N have to be homogeneous on the cylinder. Okay, there cannot be any spatial inhomogeneity, which greatly simplifies the entire problem. And they are just related by two unknown constants, C phi and C sigma. Okay. The effective thermal potential in large N also has a closed form expression. Now, you might want to murder me already here, because here there's a divergent sum. So I will keep that divergent sum as it is from now on, and only talk about regularization afterwards. This sum is simply the sum over all the eigenvalues of my conformal Laplacian on a sphere. Okay, so you have the L plus 1 plus the 1/4 conformal coupling that you have, and the C sigma saddle value acts as a mass for the boson that I integrated out. Okay. This is minimized by a set of simple equations where both the two vevs, the two saddle values of the fields appears. Okay. Okay. Now let me talk about the solution that you can have to this set of equations. So first, the usual thermodynamic relation to go from mu to q in this setting is just that q is minus the derivative of my potential respect to the chemical potential, and it turns out to be proportional to chemical potential and the vev of the phi field. So that already tells me that either I have a saddle point which breaks the global symmetry, or I cannot source a charge. Okay, so in order to have a non-zero charge, I need to give a vev to my phi field, and giving a vev to this phi field in any direction you can choose is going to implement this symmetry breaking pattern, O2 into O2 n minus 1. There are two n generators which are non-linearly realized. Okay, and this is actually the classical example that you can find in books, which usually is done at the classical level with just a phi 4 potential, in which you source a chemical potential. You're going to see that the ground state is a Bose-Einstein type of condensate. Basically, there is a charge, the ground state has a charge, but is all contained in the long wavelength mode of my boson field. So that's the usual sketch of what happens for Bose-Einstein condensation. You have a population of interacting bosons, which are picked at the zero momenta wavelength. Right? This is a fancy way to saying that only the zero mode it's present, at least in this cell. And of course, Bose-Einstein condensation is Bose-Einstein condensate is a way to make a superfluid. So already you have here an idea that if I would have to use an EFT for this sector, I should use the one that already has been discussed before. There is only a slight change for the reason that now my symmetry group is O2n, so it's larger than just O2. Namely, I have a more complex spectra of fluctuation on top of this ground state. Okay, there is one superfluid Goldstone boson. This is the one that you have also in O2. Is gapless and has a speed of sound which is not 1. Is non-relativistic. The reason why it's not relativistic is that the action that I started with is not relativistic. I source an operator which is Q, which is only a component of a conserved current. Okay, so this breaking pattern also gives you an effective non-relativistic action around the ground state. You have one massive partner to this Goldstone boson, which is also known as radial mode. And then you have a set of very particular Goldstone bosons, which are gapless, non-relativistic, and gapped, non-relativistic. So for people in high energy, you say, okay, a Goldstone boson should not have a mass. This changes drastically as soon as you have a non-Lorentz invariant effective action. Okay, if your breaking pattern takes also space-time symmetry and nonlinearly realize them, then this is actually a quite generic feature. Okay, it's also a source of many puzzles which are still ongoing, namely all of these. If I want to write an EFT for this model, what should I do with this gapped mode? I should integrate them out, but then I lose the ON character of the theory because the gapless sector only have this guy and this guy. There are some things which are still ongoing work, but for the moment, this for us is not really the main task. Okay, so let's start instead by actually computing coefficients. Okay, so the system of equation that I flashed before, after some manipulation, can be recasted in these two system of equations. One computes delta as a function of my C sigma, the VEV of the auxiliary field, and the other one is a gap equation that tells me how my VEV for sigma changes as I change the charge. Okay, this is a one-parameter set of equation with Q, the parameter that I need to input. You can solve this numerically, but first you have to specify a regularization. Okay, so for numerics, the most convenient thing is to do some sort of minimal subtraction. So basically to subtract the leading divergences inside the sum and then re-add them in a theta regularized form. Okay, this at least is the standard way that people do, for example, when they compute this sort of system for monopole operators or many other example in large N. Okay, and I have here a plot for the solution. So you have the dotted line is the C sigma field, has a VEV for any value of the charge, so it's always turned on. Only at zero charge this vanishes, and it's not really linear, but sort of linear. While my scaling dimension has a q to the 3/2 leading behavior. Okay, this you can compare it with this blue line, which is the result for the scaling dimension for the free theory. In the free theory, phi to the q has a very simple scaling dimension, which is q to the q divided by 2, which is the leading term in the small charge expansion. Okay, so these are the leading terms in both cases. And what I want to do next is to go beyond, of course, this leading approximation and try and compute as many terms as I can in these expansions. Okay. Okay. So if there are no further questions, then I can go through this. So if I want to develop an asymptotic for this solution, it's actually more convenient to use a proper theta function regularized form for these sums. I can get both asymptotics using some particular formulas related to these theta functions. Namely, as the charge goes small, we have seen that also this VEV of the field goes small, so I can expand for a small c sigma, and it's just a binomial expansion. Okay, and for large q instead, we expect also the sigma field to become very large in VEV. And the correct one way to develop an expansion around that point for the zeta function is go through a Melling representation and study simply a hit kernel asymptotic. Okay. Now here, doing all of this, I'm doing some manipulations. I'm exchanging sums with integrals. I could definitely get asymptotic series just by having this mistake built in, right? So let me tell you first about the part that I'm not less interested, but let's say the one that actually sits for the small q expansion. So we can compute like a lot of these coefficients, sort of like order 25 in closed form, but then we can go numerically up to 100. We have like a good handle of this. They have a very specific form. They're all transcendental and or polynomial in pi square. And the first three have been compared also with the large N literature. So if you do normal large n perturbation theory, you're gonna organize everything in 1/n powers, and at every order in 1/n, you have a term which is leading in Q, one subleading, and one other one. They're all polynomial. This one is picking up the highest scaling in Q at each order. Okay, so that's why you can compare with normal large n perturbation theory. Now, turns out that this expansion is convergent. Okay, it's convergent on a disk of radius order 0.28. These numbers are not super precise. We haven't run that many checks in this regime, except because it was not the one that was most interesting for us. But I think it's already like quite non-trivial, because you might know that, okay, I mean, usually power series that I get at each order in 1/n, they're supposed to be convergent, but this expansion goes to all order in n, right? So I would say a priori reason that I wouldn't know why this is convergent. Of course, you might start to think, okay, there should be some diagrammatics for it, right? If I do normal large n perturbation theory, these terms are computed by some diagrams. But at least from what I've seen, there is no like, I mean, there is sort of like a class that you can single out, but I haven't seen the exact connection with a conversion of this expansion yet. So this, if we want, there's still like a room for discussions afterwards. Good. Let's go now instead to the other expansion. So in the other regime, you have the q to the 3/2, q to the 1/2, q to the -1/2 expectation that we were expecting to find. All the coefficients are rationals. Okay. Also here we can get up to quite high order. And this instead, however, it is a divergent series, and diverges actually pretty strongly with a double factorial. Okay. And so the structure matches what a superfluid EFT would give us. Maybe the fact that these coefficients are all rational also tells me that this should be a 3-level result for this EFT. Okay, even if in this computation there is no real, it's still like a 1-loop computation. But aside from that, well, we have then room to try and understand what sort of non-perturbative ambiguities should be there, what kind of resummation we should do if we want to try to extrapolate to the other regime. And especially, we should also try to understand what are these non-perturbative ambiguities, because I told you that here we should not have renormalons. We don't have QFT instantons. We have something else, which, okay, is also like not that new object, but let me just, right. So this large order analysis, we did it in a simplified version. Namely, as long as in my equation only the zeta function, this Mellin transform appears, I could actually just decide to focus on the heat trace asymptotics. The zeta function appearing in my equation is going to be just a Mellin integral of this quantity. So our idea was just simply, okay, let's try to understand what sort of correction we get at this level, and all the others should be recovered, just applying all the correct transformation. And the reason why is that this is super simple, because these coefficients are known in closed form. These are only factorially growing. This is the Seeley-DeWitt expansion for a heat trace on a sphere with a conformal coupling. They are n factorial divergent. The extra factorial comes from the Mellin integral, okay? And the Borel transform is actually computed exactly. I mean, at least if we have, if we define it such that we divide instead of n factorial by gamma of n plus 1/2. My Borel transform has poles at every multiple of pi. And so this series is generically non-Borel summable, right? So again, we have to ask, okay, do we want to sum it up on the slightly above, slightly below? Want to do something more contortion? But this is the main gist. The summation, you can go through it. You can see that, okay, I will make an ansatz for my transseries, which has the non-perturbative sectors determined by all those simple poles, right? These are just simple poles. So all of these exponential don't come with an extra series on top. And by usual means, I will introduce my resurgent coefficients. I just extracted some -1 to the k and modulus of k just to make everything easier. And the only thing left to do is to see first if I can fix these ambiguities, if I can fix this resurgent transseries. So bear in mind that, I mean, what I'm computing is at the very end is a very physical quantity, is this eigenvalue for this operator. So I would not expect to find any extra ambiguity that I cannot fix at this level. Okay. And well, this is also reflected a lot by the fact that this is a very simple object. A heat trace has so many properties that we can use to fix these ambiguities. So one can try, for example, to ask, okay, then I want it to be real on the real time axis. I can do a median summation to obtain it. I can use some Silbert type trace formulas, which are basically Poisson resummation, but for eigenvalues which are more of the sphere than of the torus. Or I can use a non-perturbative definition in terms of a Worldline path interval. Is the thing that I'm going to talk about next. But just to give you the main message, all of these three we checked and they all agree, and they just give us like a value for this transseries coefficient, which are the one of median summation. So actually, median summation just completely resolved the entire transseries. So in the time that I have left, let me talk about a bit like how you could do it with a Worldline path integral, just because I have nice pictures for it, so I wanna show it. So the main idea is, okay, I'm computing a heat trace, and you know that if I want to compute a heat kernel on a manifold, I can write it as a path integral for first quantized particle moving on my sphere, and my amplitude can be rewritten as a path integral of this form. This is a sort of a standard result. There are some problems with the fact that I'm in curved space. So there are some ambiguities which arise at if I start computing loop orders for this path integral, right? But for what we want to look at, they're actually not really relevant. And now that I have a formal object, a path integral, I could just simply try to match the transseries that I obtained by median summation with a saddle point approximation of this path integral. Okay. Now, of course, there is already something peculiar, meaning this path integral, the saddles are all geodesics on the sphere, but of course there are no stable ones. Okay, if this was a torus, then of course you would have stable trajectories. You cannot contract to a point, but here you can. So the end result is that you can set up this saddle point expansion around the loop of dimension 0, right? Like the smallest possible loop, you find your perturbative series, which is your Seeley-DeWitt expansion, factorially divergent. Then the long geodesics, which are long circles on the sphere, have a slightly as a particular character, namely all the modes around these of all the modes of deformation around this great circle. There are some, well, there is one which is a zero mode that you can imagine just because if I have a great circle on the sphere, I can just tilt it a bit. The thing that it's doing is just giving me this extra power correction in t to in the coupling constant in the time t. But you also have negative modes, okay? And that's due to the fact that you have no stable trajectories. There are always an odd number of them, okay? So you have a non-trivial Morse index for this approximation, and that always results to a plus minus I factor. That number, that the plus or minus is not defined, but it gets, it's related to the choice of summation that you do for the first, for the perturbative series, okay? The important thing is that these are purely imaginary because of these negative modes. Exactly like, well, in the transseries that I showed before, I extracted an I out of convenience, but just because I knew that that was the end result. The instanton action is just the length of the geodesic, and all the positive modes, they should add the fluctuation series on top, right? Which we don't see, okay? So here, I mean, at least is not trivial to see that this thing is one loop exact, especially because it is not trivial to define a proper scheme of computation if you for this heat kernel in curve space. So there are work that works in the dimensional regularization type of scheme, and they show that up to 3 loop there is nothing. Okay, but we believe that here there should be some sort of like more sophisticated localization argument to tell that all of these terms should all be vanishing and only the leading one is there. Now, I told you these are not, I mean, these are not conventionalists. These are also known as Worldline instantons, right? You also see them in problems of Euler-Heisenberg-Lagrangians or Schwinger effect. These are all like classical trajectory of first quantized particle, okay? And now, once this heat trace has been completely fixed, all the ambiguities are fixed, we can start to do some, we can try to see what happens like to objects like my thermal potential or even my scaling dimension, right? So for the scaling, for the thermodynamical potential is actually quite easy. It's just a Mellin transform, so you can get you can get an exact integral form for this quantity. All the instanton parts, which are purely imaginary, just cancel out the residue on the integration path in that integral, so that boils down to just have a principal value integral. That's not much more than that. And we also check that this expression that we compute upon resumming the large charge expansion is matching the small charge expansion as well as the numerical result to like pretty good accuracy. I always believe that one can do better, but we haven't really had the motivation to better than getting to like 8 significant digits. Now, the non-perturbative correction appearing in my scaling dimensions that are slightly more complex in the sense that now we have a change of variable, right? So everything over there is in terms of this sigma field vev, and now I have to trade it with for my dependence in the charge. This is again a very ugly change of variables. But we don't, of course, we don't expect any other ambiguities to arise. We also suppose that, like, if one did the analysis directly on my perturbative series in delta, no further ambiguities should arise. So everything should be fixed already at the level of that heat trace that I showed you. And for this case, we find like a leading non-perturbative correction, which goes e to the -2 to the square root of q. This is a 2m factorial growth, so now it's square root of q. And generically, though, you would have a perturbative series on top of this, or at least in my scaling dimension, exactly because of this change of variable. However, they should all that we didn't work out exactly that whole structure, because at the time, at least for this model, we had already this simple computation that could go through. Now we are finding other double scaling limits for other CFTs in which that heat trace is not at all that simple. So at that point, it's probably just more useful to do the entire analysis at the level of the scaling dimension. So we are now trying to developing that. And well, at least in this model, you see that for order of q hat order 1, these are very small. So they are sort of telling me that my large charge expansion should work at least up to order q to the q of order 1. and having this very early onset of the superfluid behavior. Now you might tell me, okay, this is a Q divided by N, right? So what I'm really telling you is that a Q order N, okay? So a very crude extrapolation, maybe it's too crude to say that this is also the reason why in the O2, in the O2 model, you get such an early onset, but it's sort of gaining like circumstantial evidence that basically this superfluid behavior has a extremely early onset and can be extrapolated up to very low, very light operators, okay? And with these, just give me my summary and conclusion. So what we did here, the main message that you should take is basically we are doing this computation for scaling dimension of CFTs in 3 dimensions. And we are doing them in this specific double scaling limit and trying to observe these superfluid EFT predictions and trying to go beyond that by studying the large order behavior of this expansion and so on. So what we find is that the regime in which ordinary large germ perturbation theory gives you your series is actually a convergent one, while it's the one dominated by the superfluid EFT is as a factorial growth, stronger than a normal factorial growth that you would find in QFT, but because this is not really a QFT problem. Moreover, is also not Borel summable, as you've seen. I mean, at least for my heat trace, I have singularities on the real axis, but a median summation seem to completely determine the end result. So in a sense, this could be like an example of this strongest resurgence that was mentioned yesterday. And finally, we also have interpretation for this non-perturbative correction in terms of Worldline instantons. Worldline instantons which have, for particle, which have a gap order square root of Q. Now, all the Goldstone bosons that I show you, the massive one in the spectrum, have a gap of order square root of Q. So the naive interpretation of why this non-perturbative correction arises is that as I make my superfluid dilute enough, all of these modes goes gapless, and my EFT is starting to break down. Okay? So we are sort of like thinking that this should be the mechanism behind it. And with that, I will end. Thanks for your attention.
Are there questions for Nicola?
Just about the mentioning of when you said the fluctuations, when you were calculating the Worldline.
Yeah, no. It's the AC.
You said, okay, that you should see them all hopefully canceling, because the other result was just the first term of all the exponentials, right? So when you did the second calculation for the exponential piece,
yeah, for the heat trace, just for the heat trace, yes.
There you say that you have 1 plus corrections, which are the fluctuations.
Yeah, okay.
You're saying that they should somehow vanish.
Yes.
Have you managed to see anything like hinting towards that vanishing?
So the thing that we did, it was to try, we did try to make that computation in a scheme which was probably an unhappy one and was not really working as we expected. They were not vanishing in that scheme. But there are these other computations. Instead, they use like I mean, there are no divergence for this path integral, right? But there are only like ambiguities when you do perturbation theory, because you have all distributions and you have to evaluate it at coincident points. You have to sort out that ambiguity, and for that you need a scheme. And from like there is one paper that I found that was saying that exactly in a dim reg type of regularization, up to 3 loop, there is nothing. But there is no, that I've seen from the Worldline formula, there is no proof that that will be the case. The only hint that we had was exactly the resurgence structure that we get from the perturbative part.
Okay, thank you.
So just to understand this large Q hat regime, no? It looks to me that this is essentially like the Euler-Heisenberg
It's very similar, yeah.
large electric magnetic field. So whenever you have an expansion in a large external source, well, anyone, sometimes you get it's precisely the same, no? So you have 2n factorial and the Worldline instantons are responsible
Yeah,
for the.
I mean, I think this is a classical example exactly of, I mean, this delta in the end.
It's the same.
Yeah. I mean, this delta, you can think of it as an effective action. You integrated out some fields, right? And you have log that, which is your effective action, and that's going to have singularities every time your equation of motion have a 0. So every time you have a classical solution for your equation of motion, you're going to find that. So it's a very similar mechanism. The only thing is that is in curve space, and you have the particle is massive only because I have a source of finite density, as otherwise would not. But the principle is really identical.
Any other questions?
So the numbers you showed us for the inverse Q hat expansion, they don't really suggest a divergent behavior. So factorial sets on very late.
It sets on quite. Which order we even look at? Let me think. So these one in particular, they don't look that much as they're growing. They set up. I mean, I believe they don't set up that late. I think it was actually already at the order of this q to the -5 half. Of course, here is still it's still a bit unclear numerically, but I can I actually had more plots that in the end I didn't include, but I can show that.
Any other questions?
You could have done this for any sphere.
For any sphere,
not just S2.
Yeah.
So what happens in odd dimensions?
In odd dimension. So in odd dimension, how it works was, I think there was someone that did that. There was a work on it for like for a four-dimensional model in which you end up with S3. So with S3, it works much like a torus, right? I mean, if I remember correctly, you have actually works much. You have the perturbative series is trivial, and then you have the non-perturbative sectors, which don't have zero modes in that sense. They are real non-perturbative contributions, and there you cannot run an analysis of this sort, I guess, because there is no. You have to proceed like if you were on a torus, right? And just have a skip the entire research analysis part and do directly the Worldline path integral. You know that you have these saddles of long geodesics, and they're going to give you this one loop exact real contributions. But yeah, I think that's the structure that you should see.
So in four dimension, which CFT is it?
No, in CFT, this in four dimension you cannot do it. I mean, this the only integer dimension is 3 here for the CFT, right?
Oh,
I think it was actually either large enough QAD and you look at monopole operators, they have quite a similar behavior. Was either that or no? I think it was that. Yeah, I think it was that because now it's the only one that comes to my mind. But I'll check actually.
All right, let's thank Nicola again.